This is Professor Corey from the Professor's DuBois, and this lecture is our third lecture for chemical equilibrium. In our previous lecture, we learned how to use ice tables to determine equilibrium concentrations of reactants and products for a chemical equilibrium, and also how to calculate the equilibrium constant, which we represent with a capital K. We can break down our ice table calculations into three categories. The first is when an equilibrium concentration for either a reactant or product is given. In this case, we can use the concentration along with the initial concentration and the change to solve for x and easily determine all of our equilibrium concentrations and the equilibrium constant. The second category is when the equilibrium constant is provided and we are able to use the square root function. This is written in this slide, and this will work if the initial concentrations for the reactants are the same. The last category involves using the quadratic equation. Here is an example for you to try. For this problem, we do have an equilibrium concentration, so the quadratic equation is not needed. The answer is provided in the lower right. If you do not get this answer, make certain that you solved for k and did not stop when you found the value of x. This problem gives us the equilibrium constant and the initial concentrations. Since the initial concentrations are not the same, we will not be able to use the square root to simplify the calculation, and it appears as though we will have to use the quadratic equation to solve it. However, if we take a good look at our equilibrium constant, realize the value is less than 1 and it's actually very small. So this means that at equilibrium, this reaction is reactant favored. Now let's think about that. If the equilibrium is greatly reactant favored, this means that the change would be very small compared to the initial concentration of the reactants. The products, though, start at 0, so any change will be significant to the product. Based on this concept, we can make the assumption that the change in the reactant concentration is insignificant relative to the initial concentration. The rule that we will use to make this assumption is that if the K value multiplied by 100 is less than the initial concentration of the reactants, we can assume that at equilibrium, the reactant concentration will be the same as the initial concentration. Let's take a closer look at how this will work. We have an equilibrium reaction shown with the double arrows. Next, I check the states to see if there's any solids or liquids present. These would be left out of the equilibrium equation, and this example is all gases. Notice the K value. It is very small. If I multiply this by 100, it is still much smaller than the initial concentrations provided. Next, we set up our ice table. We have the initial concentrations, and since the K value is so small, we will say that the change is insignificant, so we can use the initial concentrations as our equilibrium concentration. For the product, we represent the change in terms of x. Since the balanced equation has a coefficient of 2, the change will be plus 2x. Some of you are probably wondering why we have determined the change insignificant for the reactants and not the products. To help understand this, imagine that Professor Victoria has a giant jar of jelly beans. You're thinking of a large jar, but think bigger, like a 55-gallon drum of jelly beans. I, on the other hand, have no jelly beans. If she were to give me one jelly bean, it would be insignificant to her, but to me, it would be significant. In our reaction, we have no product, so any amount produced is significant. This will make our calculation much easier because we will not have to use the quadratic equation. Solving for x gives us 7.07 times 10 to the negative 5. Hopefully you can follow my math. Now let's analyze this result. If x is 0.0000707, and we subtracted this from the initial concentration, so 0.200 minus 0.0000707, we would get 0.1999293. Report this to three significant figures, and we have 0.200 molar. This proves that the change was insignificant for the reactants. Another test we could do, and most likely won't, is solve the problem using the quadratic equation. I'll leave that one up to you. Here is one for you to try. It is somewhat scaffolded, and the answer is provided. In this problem, we're simply looking for the equilibrium concentration of the product. Oftentimes, the equilibrium constant is known, and we also know the concentrations of reactants and products. We can determine if we are at equilibrium by calculating the equilibrium constant at those concentrations and comparing it to K, except we can't really call it an equilibrium constant because we're not sure if we're at equilibrium, so we're just going to call it a reaction quotient, and this is designated with a capital Q. But realize the calculation is exactly the same, and if Q is equal to K, then we're at equilibrium. Most often with these types of questions, we're not at equilibrium, and the question will ask how the reaction will change to achieve equilibrium. If our Q value is less than K, it'll have to increase in order to reach equilibrium concentrations. The only way Q can get larger is if the product concentrations increase. These are in the numerator, and the reactant concentrations would have to decrease. Likewise, if Q is larger than K, the value will decrease, and this can only happen if the reactant concentrations increase, as these are in the denominator. If this is confusing, it may help to just make up some numbers for a simple reaction like A goes to B, just to convince yourself. Here's a problem for you to try. It's been set up for you. Notice the subscript P for the equilibrium expression. This simply means that pressure values are being used, and this is okay since all the species are in the gas phase. Since the calculated value with the given values is less than the equilibrium expression value, the reaction will have to shift to the right or produce more product to achieve equilibrium. This concludes this mini lecture where we discuss the assumption rule that can be used with very small values of the equilibrium constant, as well as calculating a reaction quotient that can be compared to the equilibrium constant to determine if the reaction is at equilibrium. In our next lecture, we're going to learn how changes to an equilibrium affect the species present. Stay tuned for more mini lectures on the Professor DuBois channel.